Good evening. Welcome back to the Thermodynamics basics. Today we will see the Thermodynamics second law. There are three laws: first law, second law, and third law. We will see second law and why the second law is required. In the first law, what we have seen, it is nothing but energy conservation. Energy neither can be created nor can be destroyed. From that practical point of view, one will not get any much information. So there is a need for the practical point of view, the second law. So we have many energies like mechanical energy, electrical energy, heat energy, chemical energy, and so on and so forth. But out of all, in the chemical reactions, the heat energy what we are using mainly. The second law says heat cannot flow from a cold body to a hot body. That is one way of the expressing. And the second one is, it is impossible to convert the heat totally into work. This is the most important one. Heat cannot be converted totally into work. That will be many ways it will be expressed, but the one is heat cannot be heat energy. Heat means heat energy cannot be completely converted into work without affecting system or surroundings. Always we are seeing in the thermodynamic system, surroundings and all. So this is the main. This can be said heat cannot be flow from a cold body to a hot body on its own, or it is impossible to construct a machine, self-acting machine, which transfers from heat from lower temperature to higher temperature. All spontaneous reactions are thermodynamically irreversible. These are the different forms. So one has to remember those forms. But main is you cannot convert the, particularly if you see in the power plants and all, what we have thermal power plants, the efficiency will be around 30 to 40%. That means heat cannot be converted into work fully. This is this way. Okay. From this, what we are going to get, anything we are going to get from this, if you see further, all our so far reactions are the isolated system. But most of the reactions what we are dealing in the practically is either in the open system or in the closed system. So there, along with the enthalpy, there is a change of entropy, both entropy and enthalpy. So neither entropy nor enthalpy can give a full picture about the spontaneous reactions, or whether reaction will take place or not. It is not able to tell completely. Now in this situation, Gibbs, the scientist, has given a new thermodynamic function, which is an extensive function. It is an extensive. That means it depends upon the quantity, and it is a state function. What he has given, he has introduced a function as the G. That is, G is a Gibbs free energy is equal to H minus Ts. This is the most important equation, and which is the more value in the practical point of view of the thermodynamics and thermochemistry and all. Of course, H also. So if you are differentiating, delta G equal to delta H minus T delta S minus S delta T. That is the differentiation. So if I am writing this G system, everywhere a system I can write delta G system at constant temperature. If I am taking constant temperature, means delta T is equal to 0. Delta H minus T delta S. System always writing is slightly bore, so we are removing. This is the equation of the Gibbs, or Gibbs free energy, or Gibbs equation. So okay, fine. From this, what we are going to find? Yes. So this is here directly for the basics. If we can say the spontaneous and all, if delta G is negative, it is spontaneous. Single. There is no exceptions. If delta G is positive, it is non-spontaneous. So how we will apply for this equation? Carefully see case 1, case 2 like this. Just slightly please try to understand more carefully. Delta G is equal to negative, it is spontaneous. Now how it is possible? Earlier we have a problems with all exothermic reactions. Initially we thought that are spontaneous, but there is one reaction where we have failed, that is though the enthalpy is positive, it is a spontaneous. Similarly, delta S is positive or spontaneous, but even negative also some reactions are there where it is spontaneous. Now we will see all those things we can overcome. Now how to work? First I will take case 1. Case 1, what is that? Delta H is negative and delta S for spontaneous positive. So here it is total negative and negative, total negative, delta G is negative. So this is a simple case, case 1, very simple, nothing is ambiguity. Now second case I am taking, delta H is negative. Now delta S I am taking as negative. If delta S is negative, it should be spontaneous. It should not be spontaneous at all. But there is again this formula I will explain very nicely. Delta H is negative. Suppose if delta H is negative, delta S is positive also, T delta S is smaller than delta H, then entire this thing will be negative. Please remember or understand, try to understand once again. Delta H is negative, but this is more value. T delta S is positive, means negative towards equal to positive, but entire this thing will be less. So that means though delta S is negative, if T is small, spontaneous. That means reaction will take at that low temperatures. Meaning is reaction will take place at low temperature. If T is more, it is non-spontaneous. That means delta H is less, T delta S is more. T is more high, non-spontaneous. I think you understand. So similarly, all the other varieties of this thing, delta H negative, both are positive. You take another case. This is positive, this is positive. That means delta H is positive, delta S is positive. In this case, the T delta S should be more than delta H. That means delta H, T delta S should be more than delta H. Then it will be spontaneous if both are positive. So similarly the other cases, T delta S value is to be taken, delta S, and multiply with the temperature, value is more than the delta H, it will be the negative in this case. Suppose the fourth case, T delta S is also low. That means delta S is positive, this is negative, but this is positive, that is non-spontaneous. TDS is more, TDS is more, here TDS is less. So like this we can see. Then one more we will see. Here important one is this delta G reaction at standard state related to minus RT ln K, where K is an equilibrium constant. From here you will come to know how much percentage can be converted from reactants to products. So this is another important in the chemical reaction. ln K RT, this is equivalent to delta H minus delta D also. This can be equal to delta H minus T delta S also. So from here you will come to know how much is the percentage conversion, or at what temperature the reaction will occur. Those conditions also will come to know. This is another reaction given by the Gibbs. So variety of reactions this can be seen. And the last one also we will complete today. That is very simple. The third law. What is third law? Third law is very simple, but no very practical, less practical use. This thing is at absolute zero, that is absolute K, that is minus 273.14 degrees Kelvin is 0 Kelvin. See, 0 Kelvin. Entropy is 0 for crystalline substance. Entropy is 0 for crystalline. Why crystalline? There is no randomness, there is no vibrations or rotations or any of the molecules between the atoms and all these things also. So that is third law. They are having less use, but in the superconductors type or super cooling cool liquids, those types it will be. In the higher classes we can see what is the most important thing in the third law of thermodynamics. But the third law is only just law. It has a 0 degrees absolute 0. The entropy approaches 0. Tomorrow we will see the problems on the this thermodynamics. Thank you.